Hello, my name is Matthew Tomowitz, and this is my Data 620 final project. So for this project, we're going to be using the 20 newsgroups dataset, which consists of 18,000 newsgroup documents, which are each a part of one of the 20 eponymous newsgroups. We're going to be evaluating different text encoding methods. Specifically, in recent years, advancements in machine learning, natural language processing, and transformers have led to a large number of encoding models, which claim to produce numeric representations of text, which effectively encode their underlying meaning. It's claimed that these embeddings are a better representation of the underlying documents than more traditional methods, such as TF-IDF, and we are going to be using community detection to evaluate this claim. We're going to be considering TF-IDF as our baseline method, and we will be looking at two sentence transformer models, the All-Mini-LM L6 V2 model, which is a well-established model that's been around for several years and is well regarded, and a newer, more state-of-the-art model, the BGE Base English V1.5 model. So we are going to be encoding each of the documents using each of these methods, and then we will be constructing graphs from these documents using k-nearest neighbors and cosine similarity, upon which we will be conducting community detection using a variety of methods and then evaluating the results. So the initial data set is very well known. We will not be doing extensive analysis upon it because of that. Traditionally, the documents consist of a body, header, footers, quoted previous documents, and then the document text itself. We are going to be strictly encoding the document body, as the headers, footers, and quoted documents contain references to other texts or the other texts themselves, as well as author names, things that are highly informative of the underlying graph structure. As we are trying to simply evaluate these encoders and the embeddings they produce, these kinds of hints, which are not consistent across all of the news groups, add a confounding variable that we are seeking to eliminate. They further don't add a significant additional variable that can be measured. So for that reason, they're being excluded. The graphs themselves could be constructed using some of this information to produce a quote-unquote more authentic representation of the underlying data. However, once again, that's another confounding variable. So we will be strictly constructing the graphs based on the produced embeddings. As we can see, the underlying data set is what we would expect. It is the well-known data set. There's nothing particularly remarkable about it except for the alt-atheism, talk politics miscellaneous, talk religion miscellaneous groups have a meaningfully smaller number of documents. However, we've chosen our evaluation metrics specifically with this in mind, and so we will not be needing to address it. Going through our embedding generation code, it's fairly standard and uninteresting. Of particular note is the dimensionality of the outputs for each of these encoding methods, with TF-IDF obviously having significantly larger number of features and the embedding models having significantly smaller numbers of features. This is really important as when training deep learning models, memory can be a significant limiting factor. Therefore, denser representations that contain a similar amount of information are highly desirable, as that significantly increases the number of documents you can train on and decreases overall training time. The graph construction, as mentioned, will strictly be based on the embeddings themselves, as we are using k-nearest neighbors and cosine similarity. The underlying graphs should be fairly different from each other, given the high dimensionality differences we see, as well as the different emphasis the different encoding methods put on the underlying data. So we would expect to see meaningfully different graph structures, and we do end up producing that. So we can see that the TF-IDF and BGE graphs in particular are relatively similar. All the graphs obviously consist of all nodes and a reasonable number of edges. They exhibit similar average degrees, although the average degree of the mini-LM model is slightly higher than the others. Of particular note is the similarity between the TF-IDF and BGE embedding graphs. Both are consist of significantly more components than the mini-LM model, and the largest connected component is a measurably smaller portion of the overall graph. Given these initial statistics, it would appear that the TF-IDF and BGE encodings produce relatively similar graphs. However, as we will see, there is meaningful difference in the underlying graph structure. While the degree distribution remains similar across both models, with the mini-LM model obviously exhibiting some differences, we can see the clustering coefficient is very different between the two graphs, with the TF-IDF graph producing significantly lower clustering, and the BGE and mini-LM graphs both exhibiting a very large bump at the extreme tail that is not necessarily present in the TF-IDF encoding. So all of this information combined means that these different encoding methods have produced meaningfully different interpretations of the underlying data, and we can draw meaningful conclusions from our community detection. So as mentioned earlier, there are 20 different communities present. We're going to be using several different community detection methods in order to fairly evaluate the different encodings. The first method we will use is the Louvain method, which is a well-known greedy algorithm, very common in community detection, and is known to perform extremely well. We will also be using label propagation, which is a very common method used when labeling texts. And our final method of community detection will be using a graph neural network, specifically GraphSage, which is trained in a self-supervised manner, attempting to do link prediction, and will produce a representation of the nodes, which we will then perform k-means clustering on. The reason for including kind of a significantly more complex method is to address the claim that these transformer models produce embeddings that have either feature interactions or latent information that is in some way not interpretable by more simple methods, and a graph neural network will inherently learn any relationships that are present, and we'll use them to the fullest extent. As we will see, this actually ends up producing a very interesting result that we will dig into further on. But first, the metrics we will be using to evaluate community detection will be the normalized mutual information, the adjusted RAND index, and modularity, all three of which are standard community detection metrics. The normalized mutual information tells us the agreement between the detected communities and the ground truth. It's more accurate than strict accuracy, as it accounts for differences in numbers of clusters, as well as not being sensitive to cluster size imbalances, which, as we noted earlier, there are some present in our data. The adjusted RAND index is a complementary metric, which measures pairwise agreement between documents, and is a measure of how documents from similar news groups are clustered together. And lastly, we'll be using modularity, which is a measure of the density of edges within a community versus between communities, and indicates that communities are well separated in the graph topology. This is our evaluation code. The graph neural network we did do some hyperparameter tuning on, It's not included in this document specifically because it produces a lot of very noisy output and is extremely large, but we experimented with different hidden layers and different either hyperparameter tuning. We used binary cross-entropy loss as our loss function, which is very common for graph neural networks. And we have evaluated it using k-means clustering. So looking at the results, we see right away definitively the best performing combination of community detection and graph representation is the Louvain method on the BGE embeddings, and that is true across the board on all metrics. We can see a clear hierarchy with the mini-LM and BGE embeddings providing meaningful information gain that can be used by all methods over the traditional TF-IDF method. However, we should note there's a very interesting result in GraphSage in particular, where it significantly overperforms on the mini-LM embeddings and significantly underperforms on the BGE embeddings as compared to the other community detection methods. And this has some very interesting implications, as we can see the BGE embeddings do overall, by all metrics, provide the best underlying representation of the text. This indicates that these embeddings may actually be of such a high quality that attempting to further process them through methods such as GraphSage actually decreases the information present in the embeddings. This has a lot of implications in terms of modeling and other deep learning tasks, and can indicate that using simpler neural networks, such as a graph convolutional network, could actually be a better choice than more computationally intensive methods. So that's a very interesting area for potential further research. But to conclude overall, we can see that these sentence transformer models do live up to their claims of producing better underlying representations of text than more traditional methods. These representations are much more information dense, meaning that more documents can be included in training without losing quality. And the newer sentence transformers do appear to outperform older sentence transformers to a meaningful extent, although not significantly, and that can be influenced by the best choice of encoder can be influenced by model choice. Thank you.